Right. So as you can remember, when I introduced the concept of increasing and decreasing function, I mentioned that increasing functions can happen in two different ways. Like this, a function can increase, or like this. And I said that for these two types, the derivative is positive, right? So the derivative is positive. If you take any point and draw the tangent line, right, draw the tangent line, you can see the tangent is positive, right? And in the decreasing functions, it can happen in two different ways again, like this or this function can decrease. So what happens to the first derivative? The sign of the first derivative is again negative, right? So you can see the sign of the first derivative is positive in these two cases, right? And sign of the derivative is negative in these two cases. So this is a problem, which means we cannot use the first derivative test to determine which option is valid within a certain region, right? We cannot distinguish between these two types by using the first derivative test. The reason is that we get a positive for both types. So let's call this type 1 and let's call this type 2. Again, type 1 and type 2. Why did I say type 1 and type 2? Because you only need to distinguish between these two. Because for increasing function, the first derivative is positive. So you need to distinguish between these two. You don't have to distinguish between other two as well, right? So here again, you need to distinguish between these two only, because the first derivative test gives you negative for both types, right? Both cases. So that's why I mentioned type 1, type 2 here, and again type 1 and type 2. So there's a problem. So first you should learn what the problem is, and there will be a solution, right? And again, there are different types of inflection points. We learn what a point of inflection is. If it goes like this or like this, we call them point of inflections, which is neither a maxima nor a minima, right? So but there are another kind of point of inflections which you cannot find through first derivative test, right? It just slipped through the first derivative test. We can't even find it, right? So in order to find those types of inflection points, we will learn about inflection points later. To find them, we need another type, another test, right? So this is where we use the second derivative test to determine or to distinguish between these types, right? And to determine a point of inflections that cannot be determined using the first derivative test, right? Right, so this is a summary of what I just mentioned. F prime of x, the first derivative, is not sufficient to distinguish between type 1 and type 2, right? And not all points of inflections, we will learn about these, and we will define what point of inflection is clearly later. Not all points of inflection can be found via f prime of x. So you cannot use f prime of x to determine all types of points of inflection. There are different types of points of inflections which you cannot be determined through this test. So for the above two reasons, we use second derivative test. So this is the reason why we use second derivative test. Now, before we introduce the second derivative test, I will introduce you the concept of concavity of a function. So we will distinguish between these two types based on the concavity of a function, and we can find the concavity of the function using the second derivative test. So before we move on to that, I should introduce you the concept of the concavity of a function. Right. So basically, there are two types of concavities. One being concave upward and the other being concave downward. So let's introduce the first one. What is meant by concave upward? Right. So when the tangent line, you know what tangent line is, stays below the function. If it stays below the functions, we say that the function concaves upward. So let's look at the intuition now. Right, so these two are the cases where the tangent line stays below the function. So if I draw a tangent line, so at any point, try this on your own. If I draw a tangent line, you can see our function stays above the tangent line, right? Or tangent line stays below the function. Tangent line is below the function, right? So in this case, we call it concave upward, right? Concave upward because the function goes upward above the tangent line, right? So it moves in this direction. And also, if I take any other point, you can see again still our tangent line, our function, tangent line stays below the function. It is below the function. Even in this case, so this is a decreasing function, this is an increasing function. You can see in an increasing function like this, tangent line stays below the function. In a decreasing function like this, the tangent line stays below the function. Again, it's the same thing, right? So I'm gonna make a proof here with regard to the second derivative. So I'm going to use this graph only. You can see here what happens. Now, how do we distinguish? How do you know that the tangent line stays below the function or above the function? For that, you can. Right. So, how do you how do you determine whether tangent line stays below the function? Now, this is what I'm going to do. As you can see, if you move in this direction, if you increase x coordinate, so what happened to the tangent line? Now in this case you can see the function is increasing. Increasing function means f dash of x is always f prime of x is always positive. Sorry, this is at this point, x plus delta x. You can see this is the f prime at x plus delta x, this is the f prime at x. Now what you can see here is that if you are increasing, if the function is increasing in this way, your tangent also increases. It increases. So what does that tells us? If the tangent is below the function f prime of x plus delta x, I mean the derivative at this point must be greater than the derivative of this point. It's true for a decreasing function as well. Even in decreasing function, you can see the tangent line stays below the function. And see here, this is the gradient. Gradient is negative. At this point, still the gradient is negative, but this is less negative, right? This is highly negative. This is less negative. So you know that negative 1 is greater than negative 3. Or negative 1 is greater than negative infinity. So again, you can see the derivative here is greater than the derivative here. So it's true for both cases. It's true for both cases where the tangent line stays below the function. So this is true. So I'm going to use the same method I used for increasing and decreasing function. I take this function to the left side, so I get 0. Then I'm going to divide this whole thing by delta x, right? Then I'm going to take the limits on both sides. As delta x tends to 0, f prime of x plus delta x. This, and what about here? 0 divided by anything is just 0, so we are just taking the limit as delta x tends to 0 of 0. So what is the definition of this one? This is the definition of the second derivative, because the function has been already derived one time. So if you derive that function again, you get the second derivative. This is the definition of the second derivative. So what does that tell you? Second derivative is positive. So this implies if the second derivative is positive, then the tangent line stays below the function. Tangent line stays below the function. So this implies concave upward situation. Concave upward situation. So let me write that down here. Right. So f double prime of x, the second derivative. If the second derivative is positive, greater than 0 means positive. If this is positive, it means the function concave upwards in that particular region. Right. So in this case, the region is from x to x plus delta x. Now let's look at concave downward situation. Right. So concave downward situation, it can happen in a decreasing function or an increasing function. You can see in a decreasing function like this, the tangent occurs above the function. See, above the function. Here again, tangent occurs above the function. So tangent stays above the function all the time. So it's the same thing I'm going to use. What does that mean? Here the tangents are negative, right? This is negative, but here this is more negative. In this case, tangents are both positive because it's an increasing function, but here the tangent is like this here, but it's like this at this point, which means the tangent decreases. Tangent decreases. So the tangent at this point is less than the tangent at this point. So f prime x plus double x plus delta x is less than f prime of x, right? So if you follow through the same steps, I'm not going to write down the steps. Finally, you would get f double prime of x, the second derivative must be negative. So what does that mean? Second derivative negative implies both ways concave downward, right? So if it says that the function concave downwards, we can take f double prime to be negative. If you find f double prime to be negative in a certain region, then you know that the function concave downwards. Okay. Now let's summarize the result. Right, so the summary is, without stopping at the first derivatives test, you can find the second derivative. So this appeared since 2019 paper. Nowadays in your papers you will be given both derivatives. So first derivative and second derivative. The first thing is for you to show that it is true, right? So you will be given the derivative. So showing them is easy. Then they will ask you to find the certain points like maximum point, minimum point, and points of inflections, and the regions in which the function increases or decreases, and the regions where the function concave upwards or downwards. So these can be found using both tests, first derivative test and the second derivative test. So this would come in handy in that case. Now sign of f double prime, second derivative, if it is positive, it means concave upward. Upward positive, remember this, upward positive. Concave downward, down means negative, right? If it is negative, we call it concave downward. So keep this in mind, and we'll look at an example now. Right, so this is an example. Determine the values of x for which the following function, this function concave upward and concave downward. So let's figure that out. Now first the function is given. If the function is given, to find the concavity of the function, we need to determine the second derivative of the function. So we have to derive this twice. First derivative can be used to find the turning points and one type of inflection point. Second derivative can be found, can be used to find the concavity of the function, and also the second type of another type of point of inflection, right? So we'll get to point of inflection later. Now what is the first derivative? Dy by dx is 3x squared minus 48. Now I can further simplify this because we're going to use this to determine turning point if needed. So I can factor out 3, then I get x squared minus 16. So this is basically 3x minus 4 into x plus 4. If you want, you can use this to determine minima or maxima points. Right. Then we have to derive this again. So use this one, not this one. Okay, use this one. Derive this again. D squared y over dx squared, and that gives us 6x, right? 6x, only 6x. So this is our second derivative. So f double prime, we'll call it f double prime. Now we can check the sign of the function at different region. Now sign changes beside 0. Okay, 0 is in the middle. On the left, right hand side you have positive, on the left hand side you have negative. So first of all, we have to find the critical point where the second derivative becomes 0. So later on you will learn that the point at which the second derivative is 0 is called an inflection point. So we will learn that later. Right. So now draw the number line again. You have to draw the number line again for this x, right? Then we have x equals 0. At x equals 0, the second derivative is 0, right? Sorry, this should be 0. Then what happens? Now we can find the sign of f double prime of x. So what is sign? On this region it is negative, on this region it is positive. So we'll divide the region, and we know if it is negative, what does that mean? This means concave downward. Positive means concave upward, right? So now you can write down the region. So let me take this space to write down the answer. They are asking us to find where the function concave upwards and where the function concave downwards. So we can write this down: concave downward when x is less than 0. X is less than 0. Then concave upward when x is greater than 0. So now concave downward and concave upward. Okay. Now let's study what else can we figure out using the second derivative test, right? So we first saw that we can use the second derivative test to determine the concavity of a function. Next we'll see that you can use the second derivative to determine all turning points or stationary points in general. So you can use the second derivative to determine maxima, minima, or a point of inflections. All points of inflections can be determined, right? So actually you might think that why do we need the first derivative test to determine these turning points? Why can't we use first and second derivative test together to determine these turning points? The reason is that you need to learn how to use the first derivative test as well, like drawing a number line and all. Then you should also know how to use the second derivative test, because it starts appearing since 2019 in your paper, so it's better that you learn it now. Right, so stationary points using f double prime of x, second derivative. So we have maxima and minima. So look at this. When you have a maxima, then your tangent line stays above the function. When you have a minima, your tangent line stays below the function. So if your tangent line stays below the function, we define it as concave upward. When tangent line stays above the function, we define it as concave downward. So what happens? If it is concave up, up means positive. At this point, your f double prime of x must be positive, right? At this point, and at this point, f prime of x is 0. You know this already. Here, at this point, f double prime of x is negative because it concave downwards. Also, at this point, your f prime of x is 0. So this is a summary. So when you look at it, you know what this means, right? So the intuition is very powerful. So try to get this idea, right? So now we can use the second derivative test without going through the number line. So don't do that in the exam. Keep that in mind without going through the number line. The first derivative test, all you have to do is to find the stationary points using the first derivative test, then use those stationary points on the second derivative test to figure out whether they are maxima or minima, right? But we are not going to do that in the exam. In the exam, you use the first derivative test. So if they say that use the second derivative test as well, then you can use that. Okay. Now you learned about point of inflections. So up until now you learned about type 1 point of inflections. You can see it goes like this. Derivative becomes 0, then again the function increases. Here this is called the decreasing inflection points. Derivative is negative, 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 0, then again negative, negative, negative. Okay. Now there's another type of point of inflection where the first derivative is not equal to 0. This is also another inflection, another type of inflection occurs here at these 2 points. You can see that's why I classified it as type 2 inflections. So in this inflection also you can see here the derivative is positive, 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 positive. It's not equal to 0 at this point. Again it's positive. Here the derivative is negative, negative, negative. You can see negative, 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 negative. Comes to a certain points, then again still it is still negative. But dy by dx does not occur. Dy by dx is not equal to 0 at these 2 points. So this is also called a point of inflection. These are all points of inflections. Say points of inflection. Right? Here also points of inflections. These 2 points of inflections. So what happens at these 2 points? Here you know that f prime is 0. F prime of x is 0. These 2 can be determined using the first derivative test. What about these 2 points? At these 2 points, f prime of x is not equal to 0. You can see it's not equal to 0. It does not become horizontal. Sorry. It's not equal to 0. Non-zero value. In this case, you get a negative value. In this case, you get a positive value, and you cannot determine through the first derivative test. These 2 points, they don't appear. But these 2 points will appear. Now what happens here is that we can use the concavity here. So what can you say about the concavity? When you assess the concavity here, now here we have this points of inflection. Inflection occurs at these points. To the left of this point, the tangent is, to the left of the point, the tangent stays above the function. The function stays below the tangent. Here, function is above the tangent. Here the function stays below the tangent, function is above the tangent. Okay. what happens here? Tangent, function stays above the tangent. On this side, function stays below the tangent. Same thing. Function stays above the tangent. After the point of inflection, function stays below the tangent line. Same thing. Tangent is above, and in this case tangent is below. Now what can you see? You can see that the concavity changes. Concavity changes through the point of inflection. Here on the left hand side, the concavity is concave downwards. On the right hand side, it concaves upward. Here concave upward, this concave upward and concave downward. You can see the function stays below the tangent. Here concave upward and here concave downward. In this case concave downward, in this case concave upward. So now we are at a point where we can define what an inflection point is, truly using the second derivative. That's why we did not define points of inflections just yet, because we needed second derivative to define the point of inflections. So the points about which the concavity of the function changes are called points of inflections. Now if you think clearly, on this side you can see the tangent line stays above, on this side the tangent line stays below. So what happens at this point? At this point, tangent line and the function coincide, right? Tangent line and the function coincide at this point. Okay. Same occurs here. Also here you can see, here the tangent line stays below the function and moves, and at this point you can see the tangent line stays, coincides with the function, and if you move further, tangent lines goes above the function, right? So at this point you cannot determine the concavity of the function, because based on the given definition, you know, if the tangent line stays above, it is concave downward. If it stays below, it concaves upward. But what happens when the tangent lines coincide with the function? Then there is no such definition, right? The definition fails there. So at these points we call it's a point of inflection. Sign changes. Here the sign changes from negative to positive. Here positive to negative. Here negative to yes, this is positive to negative, then negative to positive. So how do you determine the point of inflections? To determine the point of inflections, keep in mind, so I'm not going to prove this one. At this point, the second derivative is equal to 0, right? So here again 0. At this point, the second derivative is also equal to 0. Right? This is how we find points of inflection, right? F double prime is equal to 0. So you can see that in both types, the second derivative is 0 at points of inflection, right? At the turning points, the first derivative is 0. At points of inflection, the second derivative is 0. So you can directly determine the the points of inflection using the second derivative. So let's do an example. Right. So here's an example. Determine the points of inflections of the following functions. So function is there. To find points of inflection, if you want to find the turning, the maximum points or minimum points, still you can use the second derivative test, but don't do that in the exam. To find maxima and minima, use the first derivative test. To determine the second inflection points directly, you can use the second derivative test. So I'm going to derive these two i's. If I derive it one time, so y prime is what does that mean? That means dy by dx. Okay. This is 9 into 4. So 4 cancels out. Here we get 9 next 3. Here 9x squared. So I can factor out a 9x squared. If you want, you can factor out 9x squared, you get x minus 1. Sorry. So in this case, you know that the turning points occurs at x equals 0 and x equal 1. Right? So turning points occurs at x equals 0 and x equal 1. We don't need that, I just showed you just to recap on what we learned. Then the second derivative test, x squared, we can write it as, in short, y double prime also. This is f double prime, same thing. So if I derive this again, I get, let me take out 9. If I factor out 9, it's a constant, so it doesn't matter. We get 3x squared minus 2x. Right? From here, we can take out x. So 9x, 3x minus 2. Now, points of inflections. So points of inflections occurs at these, at what points? Where dy by dx is, the second derivative is equal to 0. So points of inflections occurs where d squared y over dx squared is equal to 0. So what does that mean? That implies either x is equal to 0 or x is 2 by 3. So at these two points, I mean, this is actually the x value of the points. At these x values, we get points of inflections. Now let's see what x value appeared in the first test, right? First derivative test. You can see x equals 0 is there. So x equals 0 is actually a point of inflection. In this case, you can see it also appears here, but x equal 2 by 3 does not appear here. It doesn't appear there, right? Because first derivative test fails to determine the second type of inflections, right? It dy by dx is not equal to 0. So x equal 0 and x equal 2 by 3 are the x coordinates of the points of inflection. Therefore, the points of inflections are x equals 0, that is one thing, x equals 0, y equals 0. At the origin it occurs, then at this point, and x equal 2 by 3, what is the value of y? Right, so I found this coordinate here, at 2 by 3 minus 4 by 9 is the y coordinate. So these are the 2 points where the points of inflection occurs. Right, so thank you for watching. We'll do more examples based on this during the discussion.